So, differentiation. What we're going to look at is differentiating trig functions, okay? After we differentiate trig functions, we are going to calculate the differential of exponentials and logs, which I know we've already been looking at the differentials of exponentials in our previous chapter. And then we're going to look at the chain rule, product rule, and the quotient rule, all of my favourite rules, which are nice and easy. So, differentiating trigonometric functions. Right. The proof as to why we can have a look at by using differentiation from first principles. We don't need to know that in our exam, okay? There is a little trick to help you. I want everyone to write this down for me. Sine, cos, minus sine, minus cos. Everyone write this down, just like you would. Imagine north, east, south, west. This is what we've got going on, okay? Nice little trick for you. We're going to look at how to prove this, even though you don't need this. But for now, we've got a nice little trick. So, if we go clockwise, we're differentiating. So, let's get some colours on the go. Blue means we're differentiating. So, sine differentiates to cos. Cos differentiates to minus sine differentiates to minus cos differentiates to sine. Get another colour. Integrating, if we go clockwise for differentiating, which way do you think we go for integrating? Anti-clockwise, absolutely. So cos would integrate to sine, sine would integrate to minus cos integrates to minus sine, and minus sine integrates to cos. So if we're going to differentiate cos, using our lovely little diagram, the differential of cos is minus sine of x. Nice and simple. Okay then, so here we go. If we are differentiating sine of x, and you can see here our coefficient of x has a constant, okay? We need to multiply by the differential of that. So what I mean by that is, we know it goes sine, cos, minus sine, minus cos. Sine differentiates to cos, and then we're going to multiply it all by k. So this becomes k cos of x, kx. Oh. Okay? And then for the next one, we have the differential of cos of x. Cos of kx differentiates to minus sine, and we're going to multiply by the differential of kx. Differential of kx is k. So we're going to have k minus sine of kx. So if we have a look at some of the quick fire questions, we should be fairly confident we've been able to do these in our head. So, differential of sine 3x, okay? Everyone should be happy. We should have 3 cos of 3x. The differential of cos of 5x, we should have minus 5 sine 5x. The differential of 3 sine of 5x, well, if we have a look, sine differentiates to cos. 3 times 5 is 15 cos of 5x. The differential of 4 cos of 3x, we're going to have 3 times 4, which is 12. We know cos differentiates to minus sine, so we're going to have minus sine of 3x. The Differential of minus a half sine x. Well, minus sine differentiates to minus cos. So, how are we going to have? We're going to have minus a half cos of x. Minus cos differentiates to positive sine. Okay? And we're going to get 2 over 3 times a half, which is 1 over 3 cos a third of x. So this is a type of example that we're going to see now we know how to differentiate trig functions. Okay. A curve has the equation y equals a half x minus cos of 2x. Find the stationary points on the curve in the interval 0 is less than or equal to x is less than or equal to pi. Now, we should remember, if we're looking for stationary points, that is when our gradient equals 0. The first thing that you should have in your head is stationary points. You should be writing dy by dx equals 0, because our stationary points are found where our gradient equals 0. Then it has this equation, okay? We have a trig function in it. So the second thing I'm going to write, I know I'm going to have to differentiate. I'm going to write sine cos minus cos. I'm going to put that in there so I know what's going on. So now I'm going to write y out again. Y equals a half x minus cos of 2x. I need to differentiate this to find my gradient function. A half x differentiates to a half. Minus cos of 2x differentiates, and minus cos differentiates to sine. We need to multiply by the differential of the bracket. 2x differentiated is 2, so we're going to get plus 2 sine of 2x. Okay? So there's our gradient. If we're looking at stationary points, we're trying to find where this equals 0. So what we're going to do, we're going to put our gradient plus 2 sine of 2x equals 0. Now, what I'm about to do now is simple algebra rearranging. 2 sine of 2x equals minus a half. Sine of 2x, divide both sides by 2, minus a quarter. Okay, what do we have here right now? We have a trig equation that we need to solve, just like we did in the previous chapter. So let's look at our interval. Our interval is between 0. So now I've got to this stage. Okay? We have our interval is 0 is less than or equal to x is less than or equal to pi. Okay? But in our case, we have 2x, so we need to change our parameters of our interval. Our interval is now 0 is less than 2x is less than 2 pi, because I've multiplied everything by 2. I might go for the white colour, I don't know if you can see that. So now, to find, so I know that 2x equals sine to the minus 1 of minus a quarter. Okay? Our interval is in terms of pi, so our calculator should be in terms of radians. Absolutely. Okay, so if I find what 2x then equals minus 0.25268 blah blah blah. Okay? What I now need to find, using my cast diagram, CAST. Okay? It's given me a negative answer, but that's all right. We have 0, we have pi, we know it's going to go back round to 2 pi. Let's think about minus 0.25. Okay, this is my angle here. This is my angle minus 0.25 because I've gone back, haven't I, from 0. Okay, so now, what do I need to do? I know normally, okay, if I have sine, I normally have it here and I reflect it here, but because we have the negative, we're going to have to reflect it here, so we do the opposite, don't we? We now know that this angle is also 0.25. So now what I do is I start at 0, okay? And I go all the way round till I reach that intersection. Here we go, I've met it here. This is pi plus that answer. Okay, so it's pi plus 0.2526. So in my calculator, I'm going to multiply it by -1. Okay, so pi plus 0.25268 plus shift pi. So my first angle I'm going to get is 3.394. Okay, 27 ... And then imagine I keep going round. So I finish there, I go here. This intersection is actually 2 pi minus the 0.2526. So 2 shift pi minus 0.25268 equals, and I'm going to get 6.03050. Okay, so here are our values. Now remember, okay, I want to just find what x is. So I now need to divide these by 2. And we only want it in the region of 0 and 2 pi. So I'm going to reject the negative one now. We only had the negative one to help us out. So that means if I divide everything by 2, I'm going to get x equals 1.697 and 3.015. So I have now found my x coordinates for my stationary points. But it says find the stationary points. So if I have a point, if I have an x coordinate, what do I need to find? A y coordinate. So I need to substitute these x values into this equation to now find my y coordinate. Okay, so I'm going to have, for the first one, y equals a half lots of x, which if we use the first one, 1.697, minus cos lots of 2 times x, 1.697. Okay, it's really good to try and be, at least 3 significant figures. Here they've done 3 decimal places. Try and be as exact as you can with, these. Okay, and we're also going to have y equals a half 3.015 minus cos of 2 times 3.015. So that means my coordinates, so my y value for this is going to give me 1.82, and my y coordinate for this is 0.539. I always then think it's common practice to write down these coordinates. So our first coordinate, and if we just do to 3 significant figures, is 1.70 and 1.82, and our second coordinate is 3.02 and 0.539. Okay, so I've written my 2 coordinates. Are you ready to test your understanding? Exactly the same principle. What we're doing is finding stationary points. This is from pure 2. Okay, this is pure 2. So give it a go. Okay, so it says find the stationary points. The first thing I should be thinking, stationary points, my gradient function must equal 0. Okay? Then I've also got a sine in my y, so I'm going to write my sine minus sine minus cos, okay? Because that's going to help me solve this question. So my y equals sine of 3x plus 2x. I'm now going to differentiate this. The differential of sine x is cos x, and because it's sine of 3x, the differential of 3x is 3, so I'm going to multiply. So it's going to be 3 cos of 3x. Differential of 2x is 2, so plus 2. Now my gradient function equals 0 because that's where I have a stationary point, so I'm going to put that equal to 0. I'm going to do some rearranging, and I'm going to get cos of 3x equals negative 2 over 3. We should be very happy with that quick step, okay? Now, I have cos of 3x. Our interval says x, so I need to change my interval. So 0 is less than or equal to x is less than or equal to 2 over 3 pi. So that means 0 is less than or equal to 3x is less than or equal to 2 over 3 times 3, which is 2 pi. Okay, so that actually becomes our normal interval now, what we would normally do. So if I have a look at my CAS diagram, okay, I'm going to put into my calculator, and we're in radians, we're in pi, so shift cos of negative 2 over 3, and I'm going to get 2.3005. So I'm going to get 3x equals 2.3005, okay? If I think about, this is 0, this is pi, this is 2 pi, this is pi over 2. 2.3005, well think about it, pi over 2, 3.14 divided by 2 is about 1.5-ish, isn't it? So we know that the angle 2.300 radians is going to be here. This is our angle. Now with cos, what do we reflect in? We reflect in this line here. If we had a positive cos, we'd be reflecting in this line here. We still reflect in this line. So this is where our reflection is, and here's our angle. So how do we know what we have to do? Well, first of all, if we start at 0 and we go all the way around, we will know our angle is 2.3005. So we know that's our first one, okay? Then, if we go around, where's our next angle? Here. How could I get to this angle? 2 pi minus the answer. So 2 shift pi minus the answer is going to give me 3.98266, okay? So now I've got my values, and it's not going to go again within the interval 0 and 2 pi. So I'm going to divide these values by 3. So I'm going to get 0.7668 and 1.3276. Brilliant. So I've got two values for x. I now need to find my y coordinates. I have an equation for y, so I'm going to substitute in y equals sine of 3 times and whatever our x is, plus 2 times, again, whatever our x is. I'm not going to write them both out, okay? But when I do this, I'm going to have a set of coordinates. For my first one, I'm going to get y equals 2.279, and when I substitute in my second value, I get y equals 1.91i. So what I'm going to do now to finish off the question is write this as a set of coordinates. 0.7668 and 2.279, and then my second coordinate is 1.3276 and 1.91i. Perfect. Okay, exercise 6a. Question 7, 8, and question 9, okay? Okay, so differentiation of exponentials and logs, okay? So, again, we've already covered this, which is really nice. So, the first one, e to the x, we know differentiates to e to the x. Sine kx, we know sine differentiates to cos, we multiply by the differential of kx, which is k. So I'm going to get k cos of kx. So e to the power of kx, we know we multiply by the differential of the power. So kx differentiated as k. So we have k e to the kx. Okay. The differential of ln x is, in fact, 1 over x. Okay? The differential of ln kx is also 1 over x. Okay? I'm going to tell you why that is now. So, if we had y equals ln of 2x, using log laws, we have 2 multiplied by x, okay? So my log laws, I can rewrite this as ln of 2 plus ln of x. We should all be fairly happy with this. Ln of 2 is a constant. It's a number, isn't it? If you type ln of 2 into your calculator, you have a number. When we differentiate a number, what happens? Yeah, it disappears. It goes to 0. So when we differentiate this function, ln of 2 goes to 0 and ln of x goes to 1 over x. That's why the differential of ln kx is still 1 over x, because if we have a constant, okay? The differential of a to the power of x, okay? What is that going to give me? Well, this actually gives me a to the x multiplied by ln a. And then for the second one, the differential of a to the power of kx, we're going to have a to the x multiplied by k ln a. So we could write that as, if we wanted, as k a to the power of x ln a. Okay, very quickly work in pairs and see how many questions you can do. Okay, so number 1, 3 to the power of x. Okay, we're going to differentiate it. We multiply by ln to the base, and here in this case it's 3. So we're going to have 3 to the x multiplied by ln 3. Okay, x cubed. We know we differentiate that. 3x squared. Ln of 3x. It doesn't matter that it's ln of 3x. Okay, our differentiation is 1 over x. 3 to the power of 2x. So what we're going to have is 3 to the power of 2x multiplied by the differential of the power, which is 2, times ln 3. So times 2 ln 3. 2 to the power of 3x. Again, we're going to have 2 to the power of 3x, multiply the differential of the power, which is 3, and then ln of the base, which is 2. 5 ln x. Well, this is the same as when we differentiate 5 ln x. Ln x differentiates to 1 over x, so it's 5 times 1 over x, which is 5 over x. This is different to ln of 5x, okay, because we're multiplying it by 5. If you want to, you can take a factor of 5 out the bracket. E to the power of a half x multiplied by the differential, a half x differentiated as a half, and then e to the power of a half x. 5 ln 2x is still 5 over x. 9 to the power of t, this becomes 9t multiplied by ln of the base, which is 9. 5 multiplied by 4 to the power of x. So we know, so when it's a multiple, you can even take the multiple out and do it at the end. So we're going to have 5 multiplied by 4 to the power of x, multiplied by ln of the base, which is 4. X to the power of 4, 4x cubed. Ln of 6x, 1 over x. 6 ln of x, 6 over x. 3e to the power of 2x, 6e to the power of 2x. E to the minus x, minus e to the minus x. Okay? Okay, so if we have y equals 5 ln x, when we differentiate that, because we have a factor of 5, we can take 5 out. So we're going to take 5 out and do the differentiation of ln x. Okay? So we're going to get 5 times 1 over x, which equals 5 over x. I think I've written my notation slightly wrong here, but okay? Because we shouldn't be writing. There we go. So, I want you to test your understanding, okay? We also have a modelling question. And we have a differentiation one. Expand first, give it a go, discuss it with the people next to you. Okay, so for the first one, we need to expand. So we're going to have e to the power of x plus 2 multiplied by e to the power of x plus 2. So you're going to get y equals e to the power of x times e to the power of x. It's e to the power of x squared plus 4 plus 2e to the power of x plus 2e to the power of x. I'm going to rewrite that. Using laws of indices, e to the power of x squared is the same as writing e to the power of 2x plus 4e to the power of x plus 4. Okay? Now what I want to do is differentiate that. So if I differentiate that, e to the power of 2x differentiated is e to the power of 2x multiplied by the differential of 2x, which is 2. 4e to the power of x differentiated is just 4e to the power of x. And then 4 differentiated is 0. Done. Nice and easy. Okay, second question. A child has head lice, and his parents treat it using a special shampoo. The population P of head lice after T days can be modelled using the formula P equals 463 to the power of minus 2t. Determine how many days have elapsed before the child has 20 head lice left. So that means, if we want to know 20 head lice left, that means our population equals 20. I always write down what information they've given me. Okay, I've got a formula, I know what P is. So I've got 20 equals 460 bracket 3 to the power of minus 2t. Okay, I'm going to divide both sides by 460. So then, 20 divided by 460 equals 3 to the power of minus 2t. Okay, if I just simplify that, I'm going to get 3 to the power of minus 2t equals 1 over 23. How do I now find out what t is? I log both sides. Do I log both sides? Okay, I can rewrite this as a log, can't I? To the base 3. So I know that log to the base 3 of 1 over 23 equals minus 2t. Okay? So that means that t equals negative log to the base 3 of 1 over 23 all over 2. I'm going to literally put that in my calculator. And then I'm going to get t equals 1.43. Okay? And it says days, so what am I going to write? Days. And make sure I've, gone back to context. Okay, part B. It says determine the rate of change of head lice after 3 days. If I want rate of change, I'm differentiating. Okay, so I need to differentiate. So I know, P equals 460 lots of 3 to the minus 2t. So differentiate dp with respect to t. Okay, so when I differentiate 3 to the power of minus 2t differentiated, I'm going to multiply by the differential of minus 2t, which is minus 2. So if I do 460, I'm going to actually just write it out. So 460, 3 to the minus 2t. We're going to multiply that by the differential of minus 2t, which is minus 2, and multiply that to the ln of what the base is. In this case, our base is 3. Times ln 3. Okay, so I'm really writing it out. So this is going to give me minus 2 times 460 is minus 920, 3 to the power of minus 2t ln 3. Okay, this is my rate of change. It says determine the rate of change of head lice after 3 days. So 3 days. In this case, our t, because we know t is days, is 3. So once I've figured out my rate of change, I know t equals 3. I'm going to substitute that in. So this equals minus 920 lots of 3 minus 2 to the power of 3, because it's 3 days, ln 3. I'm literally going to put that into my calculator, and I'm going to get minus 1.39. Okay, so that means every day we're minus 1.39 head lice per day. Okay, remember I always need to bring it back to the context of the question. Okay. Okay, so now questions 4, 9, 10, 11, 12. Okay? So sometimes we have to differentiate a combination of functions. So this is a composite function where we have a function within a function. We use the chain rule for this, okay? And what you'll notice is the chain rule is very similar to what we've been doing. You know, if we differentiate an exponential, I say we'll differentiate the power and multiply by the differential of the power. This is practically chain rule, okay? The product, okay? And repeat after me. V du plus u dv. And then we have the quotient rule. V du minus u dv over v squared. Okay then, so chain rule, nice and easy. Remember, and we spoke about this before, if we had x to the power of 5, how would we differentiate that? We would bring the power down and decrease the power by 1, wouldn't we? Okay? So we should all be happy with that. Now imagine this wasn't an x. Imagine this was a box. Okay, it's the same thing, isn't it? But inside the box is a function. Okay? We're going to multiply, we're going to differentiate the bracket and then multiply by the differential of the bracket. Okay? So in this case, I never worry about this kind of formula. Just follow my lead. So we have y equals 3x to the power of 4 plus x to the power of 5. So the differential of this equals, differentiate the bracket, okay? Forget about what's inside. Just think, something to the power of 5. How do I differentiate something to the power of 5? I do, bring the power down, 5 lots of the something, decrease the power by 1, 4. Everyone should be happy with that step. Now I'm going to multiply this by the differential of the bracket. Now, the bracket, inside the bracket, 3x to the power of 4 plus x. If I differentiate 3x to the power of 4, 12x cubed. And if I differentiate x, plus 1. Okay, and I'm going to put that in brackets because I've just, that's 1. So my final answer is 5 lots of 3x to the power of 4 plus x to the power of 4, bracket 12x cubed plus 1. Nice and easy. Now there is a formula we can use, and if you look in the book, they use substitution, etc. Honestly, just do it in your head. You've got this. I believe in you. So then, are we ready? So, we differentiate. So when it says here, outer function, this is essentially the bracket. And we multiply by the differential of the bracket. So for the first one, remember, bracket cubed, differentiate that. 3 bracket squared, isn't it? Yeah? Bring the power down, decrease the power by 1. And then x squared plus 1. And then whatever they're in the bracket. We're going to multiply that by the differential of the bracket. X squared plus 1 differentiated. 2x. So if I was to simplify this, 2x times 3, this is going to look like 6x, x squared plus 1 to the power of 2. Okay? Differentiate the bracket. Bring the power down, bracket, decrease the power by 1. And then I'm just going to fill it in. And then we're going to multiply by the differential of the bracket. The differential of ln x is 1 over x. We should know this. Fact. Yeah? This equals, if I multiply this, I'm going to get 3 over x, bracket, ln x squared. Simple. Okay, now in this case, the bracket's up here. You know when we have e to the power, the power's the bracket. When we differentiate e to the x, what do we get? E to the power of x squared plus x, don't we? And then we multiply by the differential of the bracket, which in our case is 2x plus 1, because x squared plus x differentiated. 2x plus 1. So this is going to change to e to the power of x squared plus x, bracket 2x plus 1. Okay. Differentiate the bracket. 2, bracket, to the power of 1. And then we fill in the bracket. So now we're going to multiply by the differential of 2x plus 1. What is the differential of 1? It disappears. What's the differential of 2x? Oh. 2x ln 2. Okay, and then we multiply that out. So we're going to actually get God, that looks awful. Okay, we're going to get 2x ln 2 times 2 lots of 2x plus 1. I mean, I suppose you could expand, simplify, but, you know, for now it's understanding. Okay, and the last one, ln of sine x. Differentiate ln of x is 1 over x. In our case, our x is the bracket. So 1 over sine x. Okay? Multiplied by the differential of sine x. Now remember, we love this. Sine cos minus sine minus cos. Sine differentiates to cos x. If I multiply them, I get cos x over sine x, which we know is silly cow inverted, which becomes 1 over tan, which is in fact cot of x. Okay? Okay, so for the first one, sine differentiates to cos of 5x multiplied by the differential of the bracket, which is differentiate 5x, which is 5. Okay? It's the same. This is the chain rule. Sine squared of x, we know, can be written as sine of x all squared. So this is your bracket. Differentiate the bracket to bracket sine x to the power of 1 multiplied by the differential of the bracket, which is cos x. So that is actually going to simplify to 2 sine x cos x, which looks very similar to some form of double angle, doesn't it? It does, right? Oh yeah. Let's go to our favourite page. Is it page 71? Does anyone know?
I wish page 71 was an answer.
I mean, it might be in the exam. Let's go. Ah, here, page 96, sorry, that's our... Here we go, the double angle formula. Sine of 2a is 2 sine a cos a. So, this is actually equivalent to sine of 2x by using the double angle formula. Isn't that incredible? It is. Epic. Okay, and again, if we've got root x, this is actually can be written as x plus 1 to the power of a half. Yeah? So, step 1. What we have to do is bring the power down, decrease the power by 1, multiply by the differential of the bracket. Well, x plus 1 differentiated is just 1. So in our case, it is just a half x plus 1 to the power of negative a half. Okay? Which we could rewrite as 1 over 2 x plus 1. Oh, 1 over 2 root x plus 1, if we wanted to, you know? Yeah, it's very fancy. Okay, cos cubed to 2x, if we look, we can rewrite this as cos 2x cubed. Okay, that's what that means, the notation. Differentiate the bracket, something cubed. How do we differentiate? Bring the power down. 3 something squared, don't we? In this case, it's cos of 2x. Differentiate cos 2x. Cos differentiates to minus sine. So it's minus sine of 2x, but don't forget, when we differentiate cos of 2x, we've also got to multiply by the differential of the bracket, which in this case we've got to multiply it by 2. So this becomes minus 2 sine x. So we actually had to use chain rule twice. Yeah? But because remember, when you differentiate cos of 2x, here we differentiate sine of 5x. We always multiply by the differential of the bracket. Yeah? So don't get caught out by that. So if we're going to rewrite this, 3 times minus 2. Minus 6 cos of 2x squared sine of 2x. Now, we could, use double angle formula, whatever, depending if we needed to, but for now, we'll just, write it down. Okay, and then y equals e to the power of ex. Wow. First of all, we differentiate e to the x, which is just e to the x. Multiply by the differential of the bracket. Now, our bracket is what the power is. E to the x differentiated is just e to the x. Okay, when we multiply, we add the powers. This is actually going to simplify to e x e to the power of x. That's what I call magnificent. Okay, test your understanding. You got this. Okay, so if we differentiate ln of x, we get 1 over x, which in our case is x squared plus 3x plus 5. Then we need to multiply by the differential of the bracket. X squared differentiated, 2x. 3x differentiated, 3. 5 differentiated, nothing. And then I can simplify that. 2x plus 3 over x squared plus 3x plus 5. Okay? There is a bit of a rule that you can remember here in general, but I always think it's good to just understand what to do. Given that y equals the square root of 5x squared plus 1, find the differential at the point 49. So step 1, rewrite it in the form where we can differentiate it, essentially with a bracket. Square roots to the power of half. When we differentiate the bracket. A half, bracket, and then take away 1 from the power. We're then going to multiply that by the differential of the bracket. 5x squared plus 1 differentiated is 10x. I'm then going to rewrite that. A half times 10x, 5x bracket, 5x squared plus 1 to the power of negative a half. Again, you could have rewritten that in a fancy way. 5x over the square root of 5x squared plus 1. Okay? Either way is fine. What's more important now, I want you to find the differential at the point 49. So we're going to need to substitute 4 in. Okay? So I'm going to get 5 lots of, now whenever I substitute, I always use brackets. Just in case there's negatives, we don't want to lose marks. 5 lots of 4 squared plus 1. 16 times 5, 80, plus 1, 81. 20 over, and then root 81 is 9. I get 20 over 9. Am I right? Okay. Sometimes, just to confuse us, they write dx dy. Honestly, like where do they get this from? Who knows? But they do it to confuse us. So, when we want to find dx dy by dx, so to differentiate, we've got to figure out the differential and then basically we flip it. Okay? I'm going to show you how that works. So find the differential of x when 2y squared plus y. So if we know that x equals 2y squared plus y, we're going to differentiate x with respect to y. So basically we just do the same, okay, but with y. So 2y squared, to differentiate that, bring the power down, 4y, take away 1 from the power, y differentiated is 1. Awesome. So this is dx over dy. If I want dy by dx, if I did 1 divided by dx dy, I know that's going to give me dy by dx. And remember, we did this a few chapters ago. It's because 1 divided by dx over dy is 1 multiplied by dy by dx. Stay, change, flip. Okay? So, to find dy by dx, I'm going to put 1 over dx dy, which in this case is 4y plus 1. Done. Simple. Next one. It says, find the gradient of x. Find the gradient of x equals 1 plus 2y cubed when y equals 1. Okay, so we know that x equals 1 plus 2y cubed. So we're going to differentiate x with respect to y. Remember, chain rule, bracket. Free bracket, bring the power down, multiplied by the differential of the bracket, which in our case is 2. So if I do this, I'm going to get 6 bracket 1 plus 2y squared. Now to find dy by dx, I'm going to put 1 over this. 1 over 6, 1 plus 2y squared. The reason why I put 1 over is because I do 1 divided by that, okay? If this was a fraction, if I did 1 divided by that, we'll come to that bridge. Then when y equals 1, what's the gradient? I'm going to get 1 over 6 bracket 1 plus 2 bracket 1 bracket squared. 1 plus 2 is 3. 3 squared is 9. 9 times 6, 54. So my gradient is 1 over 54. So, exercise 6C. Okay, please can you do questions 4, 5, 6, 12 and 13. Anything you don't do now, you do for homework. Okay, very quickly. So, question 4 said there's a curve of the equation y equals 5 minus 2x cubed. Find the tangent to the tangent we want with the x coordinate equal to 1. Okay, step 1. How do we find the tangent to the curve? We need to find the gradient, don't we? Okay, so we need to differentiate. Differentiate the bracket, 3 bracket, bring the power down, 2, multiplied by the differential in the bracket, which is minus 2. So this actually becomes minus 6, 5 minus 2x all squared. Okay, this is the gradient of the tangent function. At the point x equals 1, okay, so the gradient of the tangent equals minus 6 lots of 5 minus 2 lots of 1 all squared. 5 minus 2 is 3. 3 squared is 9. Minus 6 times 9. Minus 54 is the gradient of the tangent. Okay? Now it says the equation of a straight line. For an equation of the straight line, y equals mx plus c. We have the gradient. We have x, which is 1. We need y, and we need c. How am I going to find y? Well, if I've got x, I'm going to substitute y. I'm going to substitute it into here to find my y. Okay? 5 minus 2 is 3. Cubed, 27. So y is 27. I'm going to substitute everything in. 27 equals minus 54 lots of 1 plus c. So 27 plus 54 is going to give me c. 81 equals c. Therefore, y equals minus 54x plus 81. Boom. Full marks. 7-mark question. Okay. Next question. Question 5. Given that... Okay, so question 5. Wait there, sorry. Okay. Next question says y equals... Oh, sorry. Y equals bracket 1 plus ln 4x bracket 3 over 2. Find the value of the differentiation function at x equals a quarter e cubed. Okay, first of all, differentiate the bracket. This equals 3 over 2 bracket, and then we're going to take away 1 from the power, half. Everyone happy? Is 1 plus ln 4x. Multiply by the differential of the inside the bracket. 1 differentiated is 0. Ln of 4x differentiated is just 1 over x. Okay? Why? Remember we learnt this last lesson. Some of you are looking at me confused. Ln 4x. I can rewrite as ln 4 plus ln x using log laws. Log of a plus log of b equals log of a times b. Ln 4 is just a number. If I differentiate a number, what do I get? 0. Doesn't just just differentiates to nothing. And if I differentiate a ln x, what do I get? 1 over x, okay? So if it's ln of ax, where a is an integer, like a constant, it's just 1 over x. If it was a ln of x squared, that's slightly different. Yeah, because x squared is now more like a function. Okay? So then, this becomes 3 over 2x multiplied by 1 plus ln 4x to the power of a half. Okay? What do I do? Substitute in, okay? So now you've done that, now you can substitute in. The ln and the e's are going to cancel, rearrange, it'll be pretty. Okay then, perfect. So, product rule, my favourite, scrap the formula. Okay, scrap the formula. Are you ready? V du plus u dv. Okay, v du plus u dv. Now, when I say du, it means differentiate u. If it says dv, it means differentiate v. Okay? Now, it doesn't matter which way your u and v are. It doesn't matter when we're using the product rule. Okay? So, here, the product rule means we have two functions multiplied together. X squared times sine x. Is that two functions multiplied together? Absolutely. We're going to use the product rule. Okay, I'm going to get some colours out. And we're going to really understand what's going on. Step 1. You realise there's a secret multiplication sign here, but because mathematicians are lazy, they don't write it. Clue. This is a product of two functions. We need to use the product rule. Step 2. Label one v, label the other u. Some people like to write this out and do this really long dragged out thing. We're going to do that just for this example. The second example, I'm going to show you how you should really be doing it. So, it goes v. The rule is v du plus u dv. Okay? So, it's very clear. It says v is the first one. What's our v? X squared, absolutely. So I'm going to write x squared. Okay, this is multiplied by du, which means the differential of u. What's sine x differentiated to? Cos x. Again, if you don't know that, write this down. You'll learn to know it soon. Sine differentiated. So this is multiplied by the differential, cos x, okay? Plus, what's our u? Sine x multiplied by the differential of v, 2x. I'm going to simplify, sort this out so it makes it look good, yeah? I'm going to write dy by dx equals x squared cos x plus 2x sine x. Okay? Now, some people like to do this, and if you want to, I definitely suggest doing this for more complicated ones, but for this one, it's quite simple. We could differentiate all of that in our head. Okay, I would highly recommend, for some though, like the next one. Here, we have product. Okay, we're going to label it V, U. And you know what we're going to do this time, because it's a bit more complicated? Well, it's not, but we're going to pretend it is, right? We're going to write V equals X, and we're going to write dV equals, what's the differential of X? 1. Then we've got our U. U equals e to the 2x, our differential of e to the 2x is 2e to the 2x, because e to the anything differentiates to e to anything, and then we multiply it by the differential of the bracket, and our bracket in this case is the power, 2x differentiate 2x 2, yeah? So, you know, I would suggest definitely doing this method for more complicated. And then you know the rule. V du plus u dv, okay? And it's just classic substitution. It's that times that plus that times that, isn't it? So, x times 2e to the x, I could write it out, plus u, which is e to the 2x, multiplied by dv, which is 1. Then we're going to write it really nicely. So we're going to get 2x e to the power of 2x plus e to the power of 2x, because it's multiplied by 1, right? Okay. The question actually says, determine the coordinates of the turning points. The turning points is the maximum or minimum points. Maximum or minimum, we should always have this in our head, only happens when the gradient function equals 0. You talk about stationary points, maximum, minimum points, anything like that, always you should think gradient 0. Gradient 0. So what we're going to do, we're going to make this equal to 0. Now you're probably thinking to yourself, how on earth am I going to solve this? Well, guess what, everyone? They both have a common factor of e to the power of 2x. What do you think I'm going to do? I'm going to factorise. E to the power of 2x bracket 2x plus 1 equals 0. So then, for this to equal 0, and people always underestimate this, I need to know, when does e to the power of 2x equal 0, and when does 2x plus 1 equal 0? When does e to the power of 2x equal 0? Does anyone know? This equals 0. E Okay, we're going to learn both sides to get rid of the e. Ln e to the 2x equals ln of 0. So then I'm going to get 2x. And then what happens when I put ln of 0 into my calculator? Math error. Absolutely. We should have spotted that anyway here. Okay? Why should we have spotted that? Because if we think about the graph of e to the power of x. Remember, it goes like this. It crosses at 0, 1, and we have an asymptote on this line. So it's never going to cross, and y is never going to be equal 0, okay? So we reject, okay? Then, the other side, nice and easy, 2x plus 1 equals 0, so that means x must equal -1/2. So determine the coordinates of the turning point. Well, so far we've only got x equals -1/2. How do we find what y equals? We substitute it back into the original equation. Absolutely. So then y equals -1/2 e to the power of 2 lots of -1/2. Okay? I'm going to leave this -1/2 e to the -1. I'm going to leave it as a exact. So my coordinates are -1/2 and -1/2 e to the -1. Okay? Or I could write it in a fancy way. -1/2 bracket -1/2e. Either way will do. Okay, 2 more examples here. But this time, not only do we have to use the product rule, we've got to use the chain rule, because when we're differentiating, okay? Step 1, b du plus u dv. Okay, it's a secret product, v du plus u dv. Okay, so you're going to do your v and your u. Does it matter which way round when we're using product rule? Absolutely not. Now, this is a bit more complicated, so what am I going to do? I'm going to write it out. Okay, so v equals e to the power of 4x, dv equals 4e to the power of 4x. U equals, remember, if it's sine squared, I need to rewrite it. Sine of 3x squared. Now, you're going to notice whenever we have a sign and a number in front of the function and it's in a bracket, we're going to have to use chain rule twice. Okay? So when I differentiate this now, bracket differentiated is 2 bracket sine 3x, and then that's to the power of 1, yeah? And I'm going to multiply by the differential of the bracket. Sine of 3x differentiated is 3 cos of 3x. Why? Because sine differentiated is cos, and then we multiply by the differential of that bracket. Yeah? 3 cos 3x. Great. I'm going to simplify this, which equals 2, 6. Sine of 3x cos of 3x. Okay, now straight away I'm looking at this and I am thinking double angle formula. Don't know if anyone's with me, I could be wrong. But I mean, I'm looking at it and I'm thinking, hold on a minute. I've got a sine, something, cos something. Now, it might not even be that. Lucky for us, we've got to show that when we differentiate, we get this. So let's not do anything rash yet. Let's just differentiate. And then we might factorise, we might not even have to use the double angle formula. Okay, so everyone calm down. Okay? Right then. Differentiate it. Here we go. So we've got all of the values. Remember, v du. I'm going to multiply these two together. You can't really see that. Let me try again. I'm going to multiply these two together, yeah? v and du. And then I'm going to add these two multiplied together. And you can see it makes a lovely, nice x, doesn't it? Beautiful. So then, here we go. v du, so I'm going to get 6e to the 4x sine 3x cos 3x plus u dv, which is going to be 4e to the 4x sine 3x squared. Perfect. Okay, now if I actually look, I can factorise some stuff out here. Right, they're both in the 2 times tables, aren't they? Boom. 2 is coming out. They've both got an e to the power of 4x. And this one's got 2 signs, this one's got 1 sign. So I can take a sign out, can't I? That is then going to be multiplied by what's left on this side, cos of 3x, plus what's left on this side, a sine of 3x. Okay? Again, the skill there, factorising, we learned that in GCSE, didn't we? It just looks complicated, but just pretend they're shapes, that's what I do. An e to the x, love heart. Cos of x, rectangle. Yeah? If you're not sure, do that. The more we become familiar with this, the better. So then, is that what we had to do? Nope. Gone wrong and no one told me. First of all, if I take a 2 out, I need to multiply this by 3, don't I? If I take a 2 out, I need to multiply this by 2. But anyway, we went wrong because the question says it didn't take out any numbers, did it? So let's just put all the numbers back in there. Right, so let's forget we did that. But if we were to truly factorise this, that's what we'd do. So if we get rid of that 2. Okay. We're going to have 6 cos and 4. Okay, so in our case, A equals 6, B equals 4. We've proved it, we've shown it. It looks fantastic. Okay? Right then. B. Okay, so we should be able to do this really quickly. Step 1, label VU. V equals x squared, dv equals 2x. U equals 3x minus 1 to the power of a half. Du equals a half bracket 3x minus 1. We take away 1 from the power multiplied by the differential of the bracket, which is 3. Okay? Then our magic v du plus u dv. V du is going to be 3x squared over 2, 3x minus 1 to the power of minus half, or you could have done 3x squared over 2 lots of that, plus 2x lots of 3x minus 1 to the power of half. So make sure you write f dash of x equals 3x squared over 2 root 3x minus 1 plus 2x root 3x minus 1. Okay? So here are 2 typical exam questions, okay? Dr. Foster's put on here, it's damn freaking hard. So watch out for that one then. Right, test your understanding, work in pairs, give it a go, and I'll go through them in a second. So for the first one, it's clearly a product because we've got 2 functions multiplied by each other. Going to label them v and u. v equals x squared, dv equals 2x, u equals ln of 3x, dv equals 1 over x. Remember? Because, sorry, not dv, du. So, v du, dy by dx equals v, which is x squared multiplied by du, 1 over x, plus u dv, which is 2x multiplied by ln of 3x, okay? X squared multiplied by 1 over x is just x, plus 2x ln of 3x. Done. Full marks. Okay. Next question. Whew. Right, we've got this. Now this is a product, but this is a product of 2 fractions. Okay? Step 1, split it up. Okay? Personally, I would write this. 1 over 6x multiplied by 1 over x minus 1 to the half. Yeah? This is my product. Then I'm going to write it nicer. Is the only word I could use here. So this is going to be 1 over 6x to the negative 1 multiplied by x minus 1 to the negative a half. Okay. This is something that I like to see. Yeah? And what do I do now? Label this. Yeah. v du times u dv. So, v equals 1 over 6x to the minus 1. dv, if I differentiate this, bring the power down, negative, maybe we shouldn't be writing in white when we're running out of space. 1 over 6, negative 1 over 6, decrease the power by 1, negative 2. U is x minus 1 to the minus a half. du, differentiate this. Okay, bring the power down, negative a half, bracket. Reduce the power by 1, negative 3 over 2, x minus 1, multiplied by the differential of the bracket. Now in our case, the differential of x minus 1 is just 1, so pretty lucky really. Then, our favourite thing to do, v du plus u dv. Okay, so v du. So this is going to be, I'm going to do it slowly, 1 over 6x to the minus 1 times minus a half x to the minus 1 minus 3 over 2. And remember, we need to write that this is the second differential. Plus u dv minus 1 over 6x to the minus 2 multiplied by x minus 1 over minus a half. Okay, I have no idea how it wants me to simplify this, but I'm just going to simplify it how I think is good. Okay, so 1 over 6 times negative 1 over 2. We know this is negative 1 over 12. X to the minus 1, we know I can rewrite here, and x to the negative 3 over 2, I'm also going to put x minus 1 to the power of positive 3 over 2. So here's my first bit. Now, I haven't actually seen the mark scheme, so we don't know, but this is what I would do. Then, obviously, I've got my plus minus, yeah? Because it's always plus, and then because we need to then do this. This is just going to be minus 6x squared x minus 1 to the power of a half, 1 over, okay? Yep. Perfect. I mean, personally, I'm going to stop there. So this is still not simplified because there's 2 fractions. We've got to take them away from each other, okay? And to do that, you've got to make them same denominator. Anyway, once you do that, the final answer is 2 minus 3x over 12x squared x minus 1 to the bracket 3 over 2. So you can see with ours, that would be completely true because on the denominator, the highest number is 12. Highest power of x is x squared, highest power of the bracket is 3 over 2, and then obviously, when we add or take away, we've got to see what do we need to do to make them common. So, we will, at the beginning of next lesson, look at how we get from here to here. And then homework due tomorrow, page 133. If you could do questions 6, 7, 8, 9, 10. Perfect. Quotient rule. I'm going to give you a challenge, okay, that we'll come back to. Can you prove the quotient rule using the product rule? Okay, that's a bit of a challenge for you all. So we'll come back to that in a second. We know that u over v can be written as u multiplied by 1 over v. Okay, so we know that we can also write this as u multiplied by v to the minus 1. We now have two products. One product, two functions multiplied by each other. Now we're going to label them v and u. Okay? So my v is u, dv is 1. Are we happy? Okay, but even though I've said it's 1, we don't know what it is. So our dv is our differential of u. Okay, because it's a function, isn't it? I know you're thinking our u. Then our u is in fact v to the minus 1. So the differential of this, we know, is going to be, because there could be a function, so du equals minus v to the minus 2 multiplied by the differential of the bracket. So it's the differential of the bracket v. Okay? So then how this looks is we know we're going to have v du plus u dv. So we're going to get minus u v to the minus 2 times the differential of v plus v to the minus 1 times the differential of u. Now they both have a v to the power of, if I take out v to the power of minus 2, I'm going to have v du minus u dv, which I'm going to write as v du minus u dv over v to the minus 2 is v squared. Okay? The easiest way to remember it, so this is the reasoning behind it. This is the why. You won't ever need to prove it. All you need to remember is v du minus u dv over v squared. That's all you have to remember. If we're differentiating a fraction, and it does matter where the u and v is, okay, and I'll show you. So, here we have our function. Y equals x over 2x plus 5. We know it's v du minus u dv over v squared. This is how we differentiate this function. Okay? Step 1. Our v is always the denominator. And our u is the numerator. So u equals x, du equals 1. V equals 2x plus 5. dv equals 2. We should be happy with that. okay? Then we also have v squared equals 2x plus 5 squared, okay? And we just substitute this all in. So dy by dx equals v du, 2x plus 5, minus u dv, 2x over v squared, 2x plus 5 all squared. We need to simplify the numerator, which is going to give us 5 over 2x plus 5 all squared. Nice and simple. Okay? So then, moving on to our second example. It says find the stationary points of sine x over e to the power of 2x. Okay, we have two functions which have been divided. Quotient rule. v, u. Our v is always the denominator. So u equals sine x. du equals, remember, sine cos minus cos x. v equals e to the 2x. The differential of v, remember, is e to the 2x divided by, multiplied by the differential of the bracket, which is the power, so in our case it's 2. And then we also have v squared, which is e to the 2x squared, which we could, if we wanted to, write as e to the 4x, okay? I'm not sure which way we're going to need it, but we just write everything down. So that means my differential equals v du, e to the 2x cos x, minus u dv, 2 sine x e to the 2x, over v squared, e to the 2x all squared. Now what I notice is actually e to the power of 4x, well, can I cancel e to the power of 2x? Okay, maybe, but if we just wait a moment, because it says find the stationary points. Remember, stationary points means the gradient equals 0, okay? So, I can simplify this, and I am going to simplify this, because they all are multiplied by e to the power of 2x. So now I have cos of x minus 2 sine of x over e to the power of 2x. That equals 0. Okay, I can multiply everything by e to the power of 2x. So then I get cos of x minus 2 sine x equals 0. I can rearrange this. Cos of x equals 2 sine of x. I can now divide both sides by cos x. So 1 equals 2 lots of sine x over cos x, which we know is tan. So 1 equals 2 tan x. Divide both sides by 2, so a half equals tan x. Okay, now I can find out what x equals. So x equals tan to the minus 1 of a half. So now remember we're in radians. So please make sure your calculator is in radians, and it's between 0 is less than x, which is less than pi. So shift tan of a half is 0.46. Now CAST. Remember this is pi 0. 0.46 is here and here. We're only concerned with between 0 and pi, so only concerned with this area. We can see there's only one solution, and that is the actual angle itself, okay? So that means x equals 0.46364, ... Okay, I'd always go to three significant figures. So this equals 0.464 to three significant figures. Okay, so we have our x coordinate. It wants to find the stationary point. We now need to find our y coordinate. I'm going to substitute this back into here to find y. So y equals sine of 0.464 over e to the power of 2 lots of 0.464. And what I'm actually going to do is in my calculator, this is currently my answer. So in my calculator, I'm actually going to write sine answer over e to the power of 2 lots of shift, and sorry, not shift, 2 lots of answer. I'm going to get 0.176927, okay, 0.177 to three significant figures. And it wants the point, so I am going to write the coordinate, which is my x coordinate, 0.464, and my y coordinate, 0.177. Okay, so that is how we've done both of those examples. Again, the only thing that's new is using this quotient rule. Everything else, these aren't new skills. These are skills we already know, and these skills are from Pure 2 right now, okay? So, I want you to test your understanding. We've got 2 exam style questions from previous papers, okay? Give them a go. Okay, so here we have 2 functions divided by each other. So the first thing, my v is my denominator, my nu is my numerator. So u equals sine 4x, du equals differential of sine is cos of 4x multiplied by the differential of the bracket, 4 cos 4x. My v is x cubed, differential of v is 3x squared, and then v squared is v to the power of x cubed squared, which is x to the power of 6. So now I'm going to have v du, so 4x cubed cos 4x, minus u dv, 3x squared sine 4x over v squared, which is x to the power of 6. Now, they all have an x squared in common. So I can take that down, cancel that. I now have 4x cos 4x minus sine of 4x over x to the power of 4. Okay, and there's your 5 marks right there. Nice and simple, isn't it? Okay. Next question, a little bit more complicated. What we find is that this is, in fact, product rule. It's not quotient at all, okay? So 9-mark question, and you've got to find the turning point and then the equation to the normal to C at the point where x equals 0, okay? So there's 2 parts to that. Okay, so now I'd like you to head over to exercise 6E, and you are going to do questions. Page 136, questions 6, 8, 9, 10, 11, and 12. So, differentiating trigonometric functions. First of all, tan, silly cow. So y equals sine x over cos x. What do we notice? We have a function that's divided first thing we should be thinking, quotient rule. VU. So, U is sine x du cos x. V cos x dv minus sine x. V squared cos x squared. Okay? And then we're going to differentiate. V du cos squared x minus u dv, which is minus sine squared x, so that's plus sine squared x over cos squared x. Okay? So, what am I going to have here? Sine squared plus cos squared equals 1. So I'm going to get 1 over cos squared x. Okay? 1 over cos squared x, we actually know, is sec squared x. Done. Absolutely amazing. Question 2. Differentiate y equals sec x. So y equals 1 over cos x. Okay? Which we can write as cos x to the minus 1, because it's to the power of minus 1. Now what we have is chain rule. So the differential of this is differentiate the thing. So bring the power down, minus 1, bracket, and decrease the power by 1. And then multiply it by the differential of the bracket. The differential of cos x is minus sine x. So then I get minus 1, lots of minus sine x, okay? Well, this actually becomes positive sine x multiplied by cos x to the power of minus 2. So that means we can put that now as a denominator. So this equals sine x over cos x squared, which is the same as sine x over cos squared x, which I could write as sine x over cos x multiplied by 1 over cos x. Silly cow. Tan x. 1 over cos sec x. Okay? So, this is why we need to be really confident with all the rules, and these questions you're only going to get all the marks if you keep going and simplifying until there's no other. Okay? So then, if we differentiate a few other trigonometric functions, the answers are here. Differential of tan is sec squared x. Differential of sec is sec x tan x, okay? Differential of cot x is minus cosec squared x. And the differential of cosec x is minus cosec x cot x, okay? Some of these you're going to need to remember. Some of these, it's, if you just remember them, it's easier. So for part A, differentiate y equals cosec 2x over x squared. Straight away, what do we have? Quotient rule. V, U. Okay? So, U is cosec 2x. V is x squared. V squared is x to the power of 4. Du. Now, cosec 2x, we know, differentiates to minus cosec x cot x. But then we need to multiply that by the differential of the bracket, which in this case is differential of 2x, which is 2. So we're going to have minus 2 lots of cosec x, okay? But remember our x is 2x. Cot 2x. And our dv differentiated is just 2x. Okay, so now I'm going to use the rule. dy by dx. V du, so x squared multiplied by all of that, so minus 2x squared, cosec 2x, cot 2x, minus u dv, which is 2x cosec 2x all over x to the power of 4. Okay? Again, we can simplify that because they all can have a common factor of x, and we could, factorize, etc. For now, it's just getting that basic. Part B, sec cubed. Okay? This is chain rule now. So y equals sec x cubed. Okay, when we differentiate this, we have a bracket. So we differentiate the bracket, don't we? So something to the power of 3 becomes 3 something squared, doesn't it? Sec x. And then we multiply that by the differential of what's inside the bracket. The differential of sec x is sec x tan x. It tells us here. Okay, if you learn these, you don't have to show them. Okay, so then, what do I get? 3 sec squared times sec is sec cubed x tan x. Okay? Okay, test your understanding so far. Give this question a go. Off you go. So, y equals sec 3x all squared. Okay, so what do we actually have here? We should have chain rule. So if we differentiate this, we differentiate the bracket, something squared becomes 2 something to the power of 1. So sec 3x multiplied by the differential of sec 3x. The differential of sec 3x is sec 3x tan 3x, and then we're going to multiply by the differential of bracket, which is 3. Okay, it's like a double chain rule. So this then, 2 times 3 is 6, sec times sec, sec squared 3x, tan 3x. Okay? Sec squared is 1 plus tan squared 3x multiplied by tan 3x. So we're going to get 6 tan 3x plus 6 tan cubed 3x. So in this case, our constant is 6 tan 3x plus tan cubed 3x. This is why it's really important to have all of those formulas, because you could easily miss sec squared here, couldn't you? Easily miss that. But if you have them all in front of you, you know then, okay, I've got to substitute it in for that. Making use of the division one, okay? The 1 divided by dx by dy is in fact dy by dx. So it says here, given that x equals tan y, express dy dx in terms of x. So we're going to differentiate tan y. Now tan differentiates to sec squared. So tan y differentiates to sec squared y. Okay? I want 1. I now need to have 1 over to get dy by dx, yeah? So dy dx is 1 over sec squared y. Okay? I know that sec squared, okay, and again, if you have all these in front of you, is 1 plus tan squared x, yeah? So this equals 1 over 1 plus tan squared x. Now remember, x equals tan y, yeah? So, I have, that should be a y. Okay, so this means I can rewrite this as 1 over 1 plus tan of y all squared. Tan y equals x. So this means that this is actually 1 over 1 plus x squared. Okay, we've just manipulated it. Now, you might think, oh, I'm never going to be able to do that in the exam. Okay, I won't know how to do that. You will know how to do it. The more we practice, the more you'll get there, okay? Show that if y equals arc sine x, then dy by dx equals 1 over root 1 minus x squared, okay? So, step 1. We know that y equals arc sine x, okay? How do we get rid of arc sine? It's the inverse. We've got to sine both sides, haven't we? Okay? So that means if I sine both sides, I'm going to get sine of y equals x. Now I need to do dx dy. Dx dy. So we're going to differentiate sine y, which is cos y. 1 over this is dy by dx, which is 1 over cos y. Okay? Now, this is the bit that's very frustrating because you're probably going to think, how on earth? Right, first of all, you've got a root 1 minus something squared. The first thing that really should pop into your head is you know that cos squared x plus sine squared x equals 1, okay? And cos of x equals the square root of 1 minus sine squared x. Okay? So now that means that my differential equals cos y is the same as writing 1 minus sine squared y. We know that sine y is x, so sine squared y must be x squared if we square both sides. So that becomes square root of 1 minus x squared, which is just what we had to prove. I would probably put that in there, that sine of y equals x. So sine of y squared equals x squared. So sine squared y equals x squared. I'd probably write that in there. You don't have to write that middle step, but it's just to show you what's going on. So with this question, we already know that arc sine of x differentiates to this. So everywhere there's an x, we're going to substitute in x squared. And then because x squared is a function on its own, that's not just x, we need to multiply by the differential. So we know that dy by dx equals 1 over square root of 1 minus x squared, which in this case is our x squared, multiplied by the differential of x squared, which is in fact 2x. So that means our answer is going to be 2x over square root of 1 minus x to the power of 4. So then, given that x equals sec of 2y, find dx dy in terms of y. Okay, so first of all, we know that dx dy, now we should just know this, okay? This is a fact we need to learn, okay? When we differentiate sec of ky, it becomes k sec ky tan ky, okay? So we should have 2 sec 2y tan 2y, okay? Nice and simple. Then part C says, hence find dy by dx. Okay, so first of all, dy by dx. Well, we have dx dy, so we're going to do 1 over it, aren't we? So dy by dx equals 1 over 2 sec 2y tan 2y. Now this is the bit that really throws people, okay? It says it wants it in terms of x. Now always refer back to the original question. What does it say x equals? X equals sec 2y. We have sec 2y, so instead of writing sec 2y, we're going to substitute in our value for x because they mean the same thing. So I'm going to get 1 over 2x tan of 2y. Okay, this is great. but we still have a y, okay, and we've got a tan. Now, we know that 1 equals sec squared minus tan squared. What's the identity? Wait. Okay, so we know, that 1 plus tan squared x equals sec squared x. Okay, now the reason this one comes to my mind straight away is, remember, we've just got to be a bit smart. Okay, we've got to use, is it intuition? Yeah? We have a tan of 2y. We've got to put this in terms of x, and it tells us that x equals sec. I need to look for a formula that incorporates x and, tan and sec. So now I need to rearrange to get tan of 2y equals. So if I rearrange this, just like, when sine squared plus cos squared equals 1, I'm going to do this. So tan of 2y equals sec squared of 2y minus 1 square rooted. Okay, that's simple rearranging there. Okay, so that actually means we know that sec squared, we write it as sec of 2y all squared minus 1. We know what sec of 2y is. That's x, isn't it? So we actually, tan of 2y actually equals, I'm just running out of room, 1 over 2x root, and instead of writing sec of 2y squared, we know that sec of 2y, so then we're going to get x squared minus 1. And there we go. I have written the differential of 1 over 2 sec 2y tan 2y in terms of x, okay? And remember, you've got to really think, you've got to be a bit smart. They've told you that x is sec 2y, so you know you're going to have to always use sec 2y to substitute in. To get rid of the sec 2y, to get it in terms of x, you're going to have to always do that. Okay, then for the second part of the question. Okay, part B. Okay, so this time we need to find the differential of this. We are going to have to use the chain rule, okay, and I think we're going to have to use quotient. Okay, so first of all, arctan differentiated. We should know what this is. We know, okay, and this is what we know, that when y equals arctan of x, okay, when we differentiate, we get 1 over 1 plus x squared. Okay, this is what we know. Oh, what is going on? Okay. So our x, okay, is this bracket. Okay. Remember, because this bracket is a function, we then need to multiply by the differential of the function. Okay, because it's chain rule, isn't it? So what we're actually going to have is, we know then that dy by dx equals 1 over 1 plus 1 minus x over 1 plus x all squared, yeah? Multiplied by the differential of this bracket. Now this bracket is a function over a function, so we should be thinking quotient rule, okay? V and u. So v du minus u dv over v squared. Okay, so let's write down, what is our v? 1 plus x dv, 1. Okay, differential of 1 plus x is 1. U, 1 minus x du, minus 1. Okay, v squared, 1 plus x all squared. So then now we're going to multiply. So v du. So I'm going to get minus bracket 1 plus x minus u dv, which is 1 minus x, over 1 plus x squared. Okay? This is probably the hardest part of the question, is knowing that that's what we have to do. Now, the skills from here on out, GCSE level, we're literally going to be expanding, simplifying. That's it. Okay? So then. Okay. So, right. I'm going to get 1 over 1 plus 1 minus x squared over 1 plus x squared. Okay, I'm just going to leave that for a second. I can't deal with that right now. Then, on the left-hand side, obviously I'm going to have minus 1, minus x, minus 1, plus x over 1 plus x squared. Okay, so first of all, what do I notice? I notice that my x's are going to cancel. So this is actually going to give me minus 2. So on my left-hand side, I have minus 2 over 1 plus x squared. Okay, so from here now, I have a denominator of 1 plus x squared. I'm going to multiply every term in here by it. Okay, so on my numerator, I'm going to get 1 plus x all squared over 1 plus x all squared plus, and then if I multiply that by 1 plus x, I'm going to get 1 minus x squared, okay? Now I need to multiply this by minus 2. Now because I'm multiplying, you can see here I've got the same numerator, same denominator. These two are going to cancel. So I'm actually going to get minus 2 over 1 plus x squared plus 1 minus x squared. Okay, if I expand that out, I'm going to get minus 2 over x squared plus 2x plus 1 plus, I'm going to get x squared minus 2x plus 1. So I'm going to get minus 2 over 2x squared plus 2. I can cancel a 2 from everything. So I'm going to get 1 over x squared plus 1. Okay? Now it's really important to note that sometimes there are definitely quicker ways to how to find the answer to the solution. Okay? If something is taking you a long time, stop, start again. Okay? Okay then, so exercise 6F, page 141. Okay, you need to do questions 5, 6, 7, 10 and 11.